All right. Well, thank you for coming to class. I appreciate it. Um, I do want to make it worth your time for coming here, and for those of you who are watching online, I want to make it worth watching the video as well. Um, so anyway, the final exam's in a few days, so I thought we would spend some time in review, and I think. Let me just give you a kind of a breakdown of the questions in the final. Okay, so there's about 55 questions total, something around there. Okay, and about 10 of them will be conceptual questions about hypothesis testing, confidence intervals, conceptual questions about statistical inference. Okay, and we'll discuss that. I've got about 5 questions going over which statistical method is appropriate to use for a given scenario. Let's see what else I have. And about 30 or so questions, no, maybe almost 40 questions. Nah. Well, and the remaining questions, there's a couple extra, but most of the remaining questions are carrying out statistical tests or confidence intervals or other forms of inference. Okay. All right. So I wanted to. So I want to go over this one right here. Which statistical method is appropriate to use in a given situation first, as I think that kind of ties our whole class together. And then we can delve into some of these conceptual topics, as well as maybe just a review of the statistical inference methods that we've covered. Okay. So actually, maybe I'll list off some of the statistical inference that we've covered. So we started off with confidence intervals, for mu, and for mu1 minus mu2. Okay, so that was chapter 6, I believe. Then we had t-tests to compare mu1 to mu2. We also had a t-test for the mean difference. Okay, so this is paired t-test. We also had the Wilcoxon-Mann-Whitney test. And the chi-squared test. chi-squared test for independent, or for goodness of fit and for independence. Okay, chi-squared test, goodness of fit, chi-squared test for independence. Oh, as well as a confidence interval for P based on P tilde, or P squiggle. Then we have one-way ANOVA. And we also had correlation and linear regression. I think this covers all of the topics we covered. So for each of these, you'll need to know how to do them. Okay, but anyway, let's go over which statistical method is appropriate to use. So we've got several of these, 1, 2, 3, 4, 5, 6, 7, 8 that I've listed here, and we want to know, well, when is it appropriate to use? So we should always start by thinking about what is our response variable. Okay. What kind of variable is our response variable? So we'll start off with. So what is it that we are measuring, and how is it being recorded? Okay. And if we have a numeric response, our methods of analysis will go one way, or we could also have a categorical response. And then we want to look at our predictor variables, okay? So a lot of times our response variable is, we're seeing if there's a relationship between the response variable and a predictor variable. So does this other variable influence the response variable that we're measuring, okay? And so if we have a numeric response, we could also have a numeric predictor. All right, numeric response, numeric predictor. So in this case, what would the appropriate statistical method be to use? Okay, we have two numeric variables, a numeric predictor, so that's one variable that's numeric, and then the response is also numeric. So when you have two numeric variables, we use no, we use correlation and linear regression. Okay, correlation / linear regression. And that would be what we did just 2 days ago. Day before yesterday. Correlation, linear regression, numeric response, numeric predictor. Okay. All right. And then we could also have a numeric response, and if it's not a numeric predictor, we could have a categorical predictor. Now there's all sorts of, there's several methods that get classified into this. So let me just, let me cover them. Actually, let me just set this here. Okay. So if we have a categorical predictor in, here, let's get one of these out of the way. We'll start off with just saying we could either have two groups or more than two groups. Okay, so if we have more than two groups in our categorical predictor with a numeric response, what method do we use there? ANOVA, yes. Okay, so we use ANOVA. So if you have more than two groups, you're going to do ANOVA. All right, and then we've got several things within this two groups, okay? We can have the groups are independent groups, or we can have paired groups. Okay, and if we have paired groups, then we would use the paired t-test. Okay, and if we have independent groups, we have a couple methods here, okay? One would just be the, so if your data is normal or normal-ish, I'm going to just write normal-ish, then you would just use the plain old t-test, or you could do confidence intervals for mu1 minus mu2. Let me just kind of put a box around that. And if you have some outliers in here, or something to indicate that it's not normal, then we would use the Wilcoxon-Mann-Whitney test. I'll draw boxes around each of these. All right, so that's if we have a numeric response, and I think this covers most of our scenarios here. Okay, we might also have a categorical response. Okay, and let's see. We'll look at situations where we just have no predictors, one variable only. And then the other situation is where we have also a categorical predictor. So if we have a categorical predictor, meaning we've got two categorical variables, categorical predictor and a categorical response, then what we would use there would be the chi-squared test for independence. Yes.
What do you mean by categorical predictor?
So we're essentially, basically we're saying, maybe I should write categorical response variable and categorical predictor variable. So we have two variables, and maybe predictor isn't the best word per se, but what we're looking for is there a relationship between this variable and this variable, okay? And, you know, sometimes we might, I think an example was, you know, is left-handedness related to gender or something, okay? So in that case, you just pick one of them to be a response and the other variable to be a predictor. So you say, well, if we ask the question, is handedness linked to gender, then probably handedness would be the response, and we want to know what's the proportion of people who are left-handed. And then we look at the predictor in that case would be gender, and we would ask, is there a different proportion of males who are left-handed than there are females who are left-handed? So in that case, we have a categorical predictor, gender, male or female, categorical response, handedness, left-handed or not. So I don't know, predictor might not be the best word because we're not necessarily trying to make predictions in that sense, but it is to see if there's a relationship between the variables. Okay, so yeah.
So it's like probability of A being the predictor given, probability of A given B, and B would be the predictor.
Yeah, if it was A given B, then B would be the predictor, yeah. In this context of having categorical variables. Yeah. Okay. And then if we have no predictors, okay, so that we just have a categorical variable that we're looking at, then we have a situation where there's only two categories, and that would be the confidence interval for P based on P tilde. And if you have more than two categories, or two or more, then you have to use the chi-squared test for goodness of fit. I suppose for the numeric response we could also have no predictors, and for that we would use just a confidence interval for mu if there's no predictor variable. So a lot of these things we're looking to see, is there a relationship between this response variable and something else? Is there a relationship between the average height of someone, of groups of people, if we're splitting them up by gender, okay? And in that case, we have a numeric response, the height of people, and is linked to a categorical, maybe I should just say categorical variable being gender, male and female, okay? So predictor may not be the best term to use, but that's what we have. Okay. So do you guys have all this down in your notes? Okay. So let me just save that, and we'll try a few exercises here. Okay. All right. So this is also in your textbook, but let's read through this. 13.2.1. It says researchers conducted a randomized, double-blind clinical trial in which some patients with schizophrenia were given the drug clozapine and the others were given haloperidol. After 1 year, 61 out of 163 patients in this group showed clinically important improvement compared to 51 out of 159 in the other group, the haloperidol. Identify the type of statistical method that is appropriate for these data, but do not actually conduct the analysis. Okay. So I'll give you a minute to think about that, or a few moments to think. So read through this and see which group is appropriate. So what kind of response do we have? What kind of predictor, if any, do we have? What would the appropriate test be? Okay. Do you guys have an idea?
Well, we have a categorical predictor
Okay, so what is our predictor?
Patients were given either drug.
Okay, yes, so we have a categorical predictor because they were either given this drug or this drug. Okay, so we've got two categories, and that's depending on which drug they received. And then what is our response?
It's a numerical response.
It's actually a categorical response, okay? It's did they show clinically important improvement in symptoms, okay? So did they show improvement in symptoms, yes or no? So we have a categorical response, did they improve, yes or no, and a categorical predictor, which drug did they receive? Clozapine or haloperidol, okay? I don't even know if I'm pronouncing that correctly. So we've got two categorical variables, and so in this case, we would use the chi-squared test for independence. Okay, so 13.2.1, we would write, this one would be chi-squared test for independence. Okay, so improvement, showed improvement. This is categorical response. And then the drug, this and this, these are categorical predictors. Okay, it's in your text on page 13.2, not page 563. Okay, I'm gonna go on to the next one here. So we'll go to 13.2.3, and it says a biologist collected data on the height in inches and peak expiratory flow, measured a measure of how much air a person can expire, measured in liters per minute, for 10 different women, and here are the data. Okay, so we've got height measurements and peak expiratory flow, PEF measurements, and we want to know, is PEF related to height? Okay, so I'll give you a moment to think about what is the appropriate statistical test in this case. So notice how height is measured and how PEF is measured. Okay, so what's our response? Yeah, so we have a numeric response. And our predictor is height. Yeah, so we have a numeric predictor. So that means, what is the appropriate test to use?
The correlation.
Yeah, correlation and linear regression. And then here it asks you to fit the data and things like that, but we won't worry about that. We'll continue on 13.2.5. Okay. It says a geneticist self-pollinated pink-flowered snapdragon plants and produced 97 progeny with the following colors: 22 red plants, 52 pink plants, and 23 white plants. The purpose of this experiment was to investigate a genetic model that states that the probabilities of red, pink, and white are 0.25, 0.5, and 0.25. What's the appropriate statistical method here?
So I'm thinking that the categorical response variable.
So we do have a categorical response, and that's the color of the plant, right? Color of the flower. So we have a categorical response, that's true.
But there's no predictor.
And there's no predictor, that's also correct, okay? There's no predictor variable, all we have is a genetic model with certain proportions, okay? So there's no predictor, but how many categories do we have for our model that we have?
We have 3.
We have 3. Okay, so we have more than 2. So we have 3 possible proportions. So that means we would use the what?
Chi-squared test for goodness.
Chi-squared goodness of fit. Good. All right, 13.2.7 goes on and it says, the effect of diet on heart disease has been widely studied. Oh, you know what, this one we actually, they made it more complicated than it needs to be. Okay, so let's just skip that one. 13.2.8, okay. Here it says, biologists were interested in the distribution of trees in a wooded area. They intend to use the number of trees per 100 square meter plot as their unit of measurement. However, they were concerned that the shapes of the plots might affect the data collection. To investigate this possibility, they counted the number of trees in square plots, round plots, and rectangular plots. The data are shown in the following table. What type of analysis is appropriate for this data? Okay, so we got the number of trees that appeared in a plot, and we're looking at square plots, round plots, and rectangular plots. So what kind of response do we have? Our response is actually numeric, okay? Because we're counting how many trees we have. Okay, so response is numeric, and it's how many trees. Okay, so we can calculate a mean and a standard deviation. If you can calculate the mean and standard deviation for the variable you're looking at, it's definitely numeric. Okay? And our predictor, quote unquote predictor, is our grouping variable, and how many we have categorical grouping variable with 3 categories, right? You can have round, square, round, and rectangular. So 3 categories, numeric response. What is the appropriate? I'm sorry? Yeah, ANOVA. We would do ANOVA. ANOVA would be the appropriate test to use here. Okay, let's look at this last one here. And it says a sample of 15 patients was randomly split into 2 groups as part of a double-blind experiment to compare 2 pain relievers. 7 patients in the first group were given Demerol and reported the following numbers: hours of pain relief. So these were the numbers for the first group. And then if I flip the page, oops. Not too far. And then the second group were given an experimental drug and reported the following numbers in pain relief, hours of pain relief. Okay, so our response is how many hours of pain relief. So that would be a numeric response. And what would our predictor be? Yeah, categorical. Okay, so our response is numeric. How many hours of pain relief? And our predictor is categorical. It's which drug did they receive? So what test would we want to use here?
Well, it's 2 groups.
2 groups. 2 groups.
And
Are the groups independent or not?
they're independent.
They're independent because we have 7 in one group and 8 in the other. We're not reusing the same patients.
The only thing that's going to figure out if the data is
Yeah, is our data normal or not? So if we look at the numbers, none of the numbers seem to be outlandishly bigger than the other, okay? So, I mean, our biggest number here is 13, but it's not that much bigger than the next biggest number, which is 8, okay? So it's not like an order of magnitude larger. And same over here, 8 is significantly bigger than 4, but I would say it's not enough for us to say that any of these are outliers. So I would just do a t-test for independent t-test here.
Just in case we're not sure about that, should we do like a normal probability plot?
You could, yeah. I mean, in a real life scenario, you could do a normal probability plot and just kind of see. But when you only have samples of size 7 and 8, it's going to be kind of hard to tell, especially if the largest number is 8 versus 4. It's a little bit tricky. Okay. You know, if you have, let's see if there's a. Oops. I did not want to go there. Trying to see if there's another set of data here. Okay, well, I think that's a good sample of some examples here to give you some exercise in which test is appropriate to use. Okay.
So for that last example,
Uh-huh.
do either a t-test or a confidence interval? Because I know that
You could do a confidence interval. That's also true. You
Okay.
could do a confidence interval for the difference between means, and you will see if 0 falls within your interval.
Oh, right.
Okay. So that's also entirely allowed. That's very, very true. Okay. I guess I also want to point out it's important to note how the variables are measured as well. Okay. So for example, if we took someone's age, we wanted to know if age is related to another variable. Okay. So let's say, is age related to, I don't know, whatever numeric variable we're measuring. Okay. In that case, if the variable we're if the age is recorded as a numeric variable, so let's say we're looking at age versus height. Okay. So we have a numeric response, which is height, and a numeric predictor age. Then correlation would be appropriate. Okay. But if we changed the way we measure age into a categorical variable, so maybe we just have age groups, and we say children ages 4 through 8, and children ages 9 through 13, or something like that. Okay. And we turn our age into a categorical variable, then correlation would no longer be appropriate, and we would have to use a categorical variable. So depending on how the variable or the predictor or even the response is measured will affect the type of analysis that should be done. Okay. So you know, when you if you fill out marketing surveys, they probably ask for your age, but they don't ask for an exact number. They just put you in demographic categories. They say, are you 18 to 24, or 25 through 34, and 35 through 40 something. They put you in these categories because the analysis is probably more appropriate that way. Okay, rather than trying to say, oh, 23-year-olds is this much different from 24-year-old, which is this much different from 25-year-olds. It's easier to kind of pick out stages of life and put people's ages into categories that way. Okay. All right. So keep that in mind. You've got a few questions in the exam about that. Okay. Go on. All right. So should I do the conceptual stuff, or should I go over the maybe just kind of an overview of all the different statistical tests? Do you guys have a preference?
I have preference on conceptual stuff.
The conceptual stuff? Okay, okay. Conceptual stuff we'll do first, and then we'll do the whatever. Okay. The statistical tests. And just because it's just the two of you here, just maybe I'll just power through as much as I can, and maybe we can finish earlier. But if you need to take a break, we'll take a break also. Okay, no worries. All right, so we'll go over some conceptual questions. Questions/topics. Okay, so perhaps we will start off with maybe just some important concepts, such as the p-value. Okay, so because this is a class on classical statistics, okay, a lot of our discussion focuses on the p-value. I think in as you study more statistics, you'll see that the thoughts on this have advanced, but we all start off with the p-value in classical statistics. And so what is the definition of our p-value? It is the probability of observing our data or something more extreme if the null hypothesis were true. Okay, so let's just let's try a few example questions. And I might ask you, what is the meaning of this p-value in the context of this problem here? Okay, so let's say we had one-way ANOVA. And we wanted to know, is the number of trees in a plot associated, or if the number of trees counted affected by the shape of the plot. Okay, and we have round plots, square plots. Okay, we'll say circular plots, circle, square, rectangle. So is the number of trees counted by the shape affected? Is the number of trees counted affected by the shape of the plot? Okay, so our null hypothesis, well, actually, maybe I won't write that. And let's just say you did your study. So you observed, 20 plots of each type. And you did one-way ANOVA. And let's say your resulting p-value was 0.16. Okay, what is the meaning of this p-value?
That we should not reject.
Okay, so our conclusion would be not to reject, but in terms of this, I think what I'm asking for is, so our null hypothesis would be that the mean of the circles, mean of the squares, and mean of the rectangles are all equal to each other. Okay? And so whatever data we observed, they probably did not have the exact same means. Okay? I mean, that's almost guaranteed. Okay? So our data did not have the same y bar for all three groups. Okay. The data is not, I didn't provide the data, I just said you observed 20 plots of each type and you did one ANOVA and your p-value ends up being 0.16. Okay? So from there, that is enough to tell us that our data didn't have the exact same y bar for all three groups. Because if the y bar was the same for all three groups, our p-value would be 1. Okay? But what this means is that, so the meaning of our p-value would be that if mu1, or if the three mu's were actually equal, okay, then a random sample of plots would have mean values as different as those we observed, or more extreme, with a probability of 0.16, just from the random sampling alone. Okay, so I know it feels a little cumbersome to read, but what that's saying is that, if they have no true difference between the three groups. So whenever we take random samples, we would expect that our random samples would have about the same mean, okay? But of course, because of random sampling, they're not going to be exactly the same. So what's the probability that a random sample would produce the values we have, or something that are more different from each other? So let's say, our three groups had a mean of 6 and a mean of 7 and a mean of 6.3, okay? So however you measure those differences there, what's the probability that a random sample would produce three groups with those differences or something more? Well, it would happen about 16% of the time just from random sampling. Okay, so the results we observed could be a result of random sampling alone, and the probability of it being of that happening by random sampling alone is 16%. So that's the definition of the p-value. Okay, so maybe it would be a worthwhile exercise to try to think of what is the meaning of this p-value in the context of this problem, okay, for the different types of tests involved, and those being, ANOVA, test for significant correlation, t-test, chi-squared test. Okay. Do you want to do another example, or is this okay? That's okay? All right. Okay, so know your p-values. Let's try, okay. All right, and we'll talk about appropriate conclusions also, okay? All right, so if your p-value ends up being less than alpha, that means what? Okay, yeah, that means we should reject the null hypothesis, okay? It also means, so rejecting the null hypothesis is equivalent to saying we accept the alternative hypothesis, okay? So rejecting the null is equivalent to accepting the alternative, okay? Rejecting the null means we have evidence to, we can also say we have evidence to do either of these things, okay? We have evidence to reject the null. We have evidence to accept the alternative. Accept or support the alternative if the p-value is less than alpha. Okay. Do not say, okay, do not say proves HA is true. Okay, because we're not proving that the alternative is true or proves that the null hypothesis is false. Okay, these are not correct. Okay, all we can say is that we have evidence to support the alternative. We have evidence to reject the null. Okay, and on the other hand, if the p-value is greater than alpha, okay, we do not reject the null. We do not accept the alternative, okay? And it just means we don't have evidence. We do not have enough evidence. We do not have evidence or enough evidence to reject the null, accept the alternative. Okay. And again, do not say we accept the null. Okay, and do not say we reject the alternative. Is that okay? Okay, so let's try an example here. Let's say we do a t-test for paired data. Okay. And let's say alpha, let's say your p-value, whatever that happens to the test, your p-value ends up bigger than alpha. Okay. So let me list off some possible answer choices here. So this means Okay, so I'm going to just list off some choices. We have evidence to say that mu1 is greater, or I'll just say not equal to mu2. We do not have evidence to say that mu1 is equal to mu2. We have evidence to say mu d is equal to 0. Okay, we'll just leave it at that. Maybe I'll label these A, B, C, D, and E.
Oh, are those the choices?
These are your choices. So which one is the correct choice? You've done a t-test for paired data. Whatever your data shows, your resulting p-value at the end of the test was greater than alpha.
I'd say C.
P-value is greater than alpha. Okay, so let's go through this. All right, so our p-value is greater than alpha. So what does that mean? That means we do not reject the null hypothesis, right? Okay. What would for t-test for paired data, what is our null hypothesis?
The difference in means is
Okay, it's actually that the mean difference, and I'm getting technical here, but the null hypothesis is that the mean difference is equal to 0. Difference in means implies mu1 minus mu2 because there's a difference between means. But here there's only one mean and it's the mean difference. I know I'm being nitpicky, but the null hypothesis is that the mean difference is 0, and the alternative would be that the mean difference is not 0 or greater than 0 or less than 0.
also for unpaired data.
Yeah, this is for paired data. Yeah, so for unpaired, on an aside, so for unpaired or independent, I should say independent groups, the null hypothesis is that mu1 equals mu2, or equivalently, that mu1 minus mu2 is equal to 0. Okay, so this would be a difference between the means, difference in means, because there's two means. Here there's only one mean, and it's the mean of the difference. I know it's nitpicky, but I would feel wrong if I allowed you to get away with this. Okay, so anyway, in our answer choices, we're talking about t-test for paired data, which is the appropriate conclusion to make. So we do not reject the null, so that means we do not have evidence to reject the null hypothesis, which states that mu d is equal to 0. Okay, so we don't have evidence to reject that. Okay, which could also be rewritten as we don't have evidence to accept the alternative that the mu difference is not equal to 0. Okay, and so the correct answer is answer choice D. This is the correct one. We don't have evidence to say that the mean difference is not equal to 0.
So why isn't it C?
Okay, so we have evidence to say this. This would be equivalent to saying we accept the null hypothesis. Okay, and that would be that's one of our no-nos, right? We either reject or we don't reject the null, and generally we never use the evidence to support the null hypothesis. We only use the evidence to support the alternative. So let me just flip back a slide. Okay, so if the p-value was greater than alpha, we don't reject the null, we don't accept the alternative, and we don't have evidence to say this or that. Okay, we only use the words we have evidence when the p-value is less than alpha. And in this case, our p-value is greater than alpha, so this is a situation where we don't have evidence.
So we can have evidence that will cause us to reject or to not accept the alternative hypothesis?
No. I think, wait, let me just make sure I'm hearing that correctly.
So in this case, we don't have evidence to accept the alternative hypothesis.
Yeah, we
That doesn't mean that the null hypothesis is correct. So we can't say that because we're rejecting the alternative hypothesis. Oh wait, because we're not accepting the alternative hypothesis, we can't accept the null hypothesis.
Correct. Yes. Just because you are not accepting the alternative doesn't mean you are accepting the null.
Right.
Okay.
So evidence.
Yeah, it's so, if you think of a criminal trial, maybe there's not enough evidence to convict the defendant. So at the end of the trial, the jury says we find the defendant not guilty. Does that prove that the defendant is innocent? No. Okay. So a lack of evidence is not proof that the person is innocent. Okay. The person might be innocent, but because there was not enough evidence doesn't prove that the person is innocent. Okay, it's much more difficult. Like at least the way the court system is set up, it's not intended where people have to prove their innocence. Okay, it's only the burden of proof falls on the prosecution to convince the jury that the person is guilty. In a similar way, for hypothesis testing, the burden of proof falls to the alternative hypothesis. Okay, so is there enough evidence to convince you that the alternative is true? If there's not, you just continue assuming that the null is true, and we never try to prove and say the null is true. We just assume that it is. Is that okay? You want another example like this, or?
I think we're good.
We're good? Okay. So be prepared for questions kind of like this, but maybe not for t-test prepared data, maybe a different statistical test here, okay? So, these conceptual questions do get a little bit, I don't know, a little bit tricky, I think, so. All right, let's talk about type 1 and type 2 error. Okay, what is the probability of a type 1 error? Yeah, alpha, our significance level, okay? And probability of a type 2 error? Is beta, okay? Alpha is the first letter of the Greek alphabet, so it's type 1. Beta is the second, so it'll be type 2. Probability of a type 2 error. Okay. And do you remember what 1 minus beta is called? This is called the power of a test. Or it's just known as power. Okay. Type 1 error. What is a type 1 error? Type 1 is our decision is to reject the null hypothesis, but the truth is that the null hypothesis is true. Okay. Again, we don't know what the truth is. We're hoping that our data leads us to the correct conclusion, and we can go through a test and do everything the right way, but our data might lead us to reject the null hypothesis just because we happen to observe a strange set of data. Type 2 error, our decision is not to reject the null, but the truth is that the null hypothesis is false. Okay. So what we're hoping for is that whenever the null hypothesis is false, is that we hope we would reject the null. Okay. But we might not have enough evidence. We might not have collected enough data to convince us to reject the null hypothesis. Okay. So regarding our choice of alpha, when would we prefer a large alpha when, and we prefer a small alpha when? Because we have a choice over alpha when we do our test. We get to choose the alpha to use. So we prefer large alpha when ... and we prefer small alpha when ... Okay, so I guess your answer choices here would be type 1 error is worse or is less worse than type 2 error. And over here we would write type 1 error is worse or less worse. Okay, so I'll give you a moment to think. We prefer a large alpha when type 1 is worse or less worse, and we prefer a small alpha when type 1 is worse or less worse. It's a little hard, huh?
Yeah.
So think, okay, well, if I increase alpha, what's going to happen to this?
Our chance of getting type 1 error will increase.
Yeah, okay. So if I choose a large alpha, what happens to the probability of type 1 error? Probability of type 1 error is high, right? Okay, so if we have a large alpha, the probability of type 1 error is high. Okay, so would we want lots of type 1 error? We would want and we're basically saying, okay, we prefer to have lots of type 1 error over type 2 error. Okay, so large alpha means more type 1 error and less type 2. So in that case, we would choose a large alpha when type 1 error is what? Less worse. Okay. So we pick a large alpha if the type 1 error is less worse, because large alpha means we're going to have more type 1 error. Okay, and so that means small alpha means less type 1 error. So type 1 error is low when we have a small alpha. So that means we would choose that when type 1 error is worse. Okay. All right, so let's try an example here. All right, so we have a test to detect, I don't know, a highly contagious disease. Okay, so in that case, when we do the test, we assume patient is disease-free. And the alternative would be patient has the disease. Okay, so in this situation, do we prefer a test with large or small alpha?
I would say small, because we don't want us to diagnose a patient or miss a diagnosing a patient. Sorry.
Okay. So ideally, so let's just talk about the ideal case. So ideal case, patient is sick. We detect disease. And if patient is healthy, ideally, our diagnosis, or we say disease-free. Okay. So maybe I should say, maybe instead of saying detect disease, we would say, we say you have the disease. Okay, so that would be the ideal case, right? Patients who are sick, who have the disease, we say you have the disease. And if the patient is healthy, don't have the disease, we say you are disease-free. Okay, so we have two errors. Okay, the errors, we have patient is sick, and we say disease-free. And we have patient is healthy, and we say you have disease. Okay, so which is a type 1 and which one's a type 2 error? Yeah, so this one is a type 1 error. And this one is a type 2 error. Okay, that's correct. Right, because we look at if the null hypothesis is true, but we reject it, which is what's happening here, that's type 1. And if the alternative hypothesis is true, but we fail to conclude that that's a type 2 error. Okay. So in this case, which one is worse?
Type 2.
Yeah. So I would argue that this is worse. So
We want a large alpha.
we would want a large alpha. Large alpha preferred. Okay, so a lot of times when we have tests to detect diseases, especially highly contagious ones, we go a little bit overboard. You know, we'd rather kind of quarantine too many people than let a sick person go out there and be a vector to the disease and spread everyone.
That's why I feel like that's a little subjective, because what if you're quarantined, what if you're also required different drugs at the end of the day?
Yeah, okay, so, all right, so it's true. With things like, if the, I don't know, if they say the cure is worse than the disease, then maybe we don't want to make type 1 error, right? So if it's like, maybe, you know, you have a disease and we're going to give you all of these drugs that will like destroy your life, maybe that's not a good thing, okay? But if it's just kind of like, well, maybe we just want to keep you in the, give you a separate room where you're not coming in contact with too many people at the hospital or something like that, and things like that. You know, like with the Ebola case, they went very, very, very cautious in terms of the people who are in contact, and maybe someone could say, well, that was unnecessary and you wasted money doing this and that, but I think it's better that, you know, we don't take risks for things like that. So, and Ebola actually isn't super contagious in terms of like it being airborne or anything like that, but because the consequences are deadly, it's better to assume these types of things. Okay. All right, so you might have a question like this regarding type 1 and type 2 error. Okay, let's talk about confidence intervals. So let's say I make a 95% confidence interval for the mean value mu, okay? And let's say the confidence interval, I don't know, this is, we're looking at the average weight of, I don't know, species of frog, okay? And so let's say our mu is, our confidence interval for mu is from 47.2 grams to 53.8 grams. Okay, what would be an appropriate interpretation for this confidence level, confidence interval? Okay, and so I'm going to just list off some possible choices here, and you pick out the one that is correct. Okay, so we are 95% confident that the average weight of our sample is between 47.2 and 53.8. Let me just see. There is a 95% probability that the average weight of the population of frogs is between 47.2 and 53.8, and we'll say there's a 95% probability that future frogs that are sampled have mean weights between 47.2 and 53.8. The mean weight of all frogs is between 47.2 and 53.8 with 95% confidence. And lastly, the weight of a future selected frog will be between 47.2 and 53.8 with 95% probability. Sorry, I had to write a bunch of these answer choices, but which one is a correct interpretation?
I'd say the second to last. Because it's based on population.
It is based on the population,
It's not based on the sample.
not based on samples or future selected frogs. That's true. Okay, so it's based on a sample. Based on the population. Okay, so this one says sample, so that's no good. And this one talks about future frogs that are sampled, so that's also not correct. And not future selected frogs. Okay, so we're down to this one. There's a 95% probability that the average weight of the population of frogs is between 47.2 and 53.8. And here it says the mean weight of all frogs is between 47.2 and 53.8 with 95% confidence.
So there's this difference between confidence and probability.
Yeah, so probability is not correct, and so we want to choose this one that says
And then why can't we say probability then?
we cannot say probability because when we do a confidence interval, okay, we are making a statement about the population. And it only makes sense to talk about probability if there's uncertainty. So we talk about what's the probability that a coin that I flip will land on heads or tails. Okay? But once the coin has flipped, there's no uncertainty, so it doesn't make sense to talk about probability there. The same idea holds here. Okay? The population, we think of the population as fixed. Population is fixed, and so the mean of the population is also fixed. Okay, there's no uncertainty regarding this quantity, the mean of the population. So it doesn't make sense to talk about probability. It is unknown to us, so we don't know the answer, but we can only talk about confidence levels. Okay, at least from a classical statistics point of view, we can only talk about our uncertainty in terms of confidence. Our not knowing.
Think of it as like we don't know. I mean, it's impossible for us to catch every frog out there for us to know what the probability is.
Yeah, it is impossible for us to figure out this number. But if, hypothetically, if we could freeze time right now and catch every single frog, this number does exist somewhere, and it's not a number that changes. It's not subject to random forces. Okay, at least that's the approach in classical statistics. Okay, other more quote modern statistics with Bayesian ideas and stuff like that is a little bit different. But from a classical point of view, this is how we treat it. We treat the population as fixed. There's no uncertainty. Just as saying, if I flipped a coin and I have it sitting on the table, it doesn't make sense to say what's the probability that it landed heads, because it either did or it didn't. You don't know the answer because you can't see the coin, but it doesn't make sense to talk about probability because the thing is determined. Okay, so. Huh? You can only be confident. You can only be confident about in your answer, and things like that. And then we can get into a little bit of just touching on philosophy. When I flip a coin, is it really uncertain, or is it just a subject to, the laws of physics and what happened with my thumb and things like that, and what is truly random, and maybe physics at some level down to the quantum level is random, but from our larger life perspective, what is that, right? So who knows? Okay. I think that's about it for conceptual ideas. Maybe I'll do a brief run through of all the different tests and.
For another conceptual question.
Okay.
Is it a possibility you may be asked based on a confidence interval for the difference in means? So as in if it has.
Oh yeah. Okay. So you did have questions on, I think, quiz 3 that related the results of a confidence interval. Confidence interval for mu1 minus mu2 to the results of a t-test for the null hypothesis mu1 equal to mu2. Okay, so I think you guys did this for a quiz, so let's just try one out. Let's say you make a confidence interval for mu1 minus mu2, Ci does not contain 0. Okay, so if you did a t-test with mu1 minus mu2 equal to 0, and the alternative mu1 minus mu2 not equal to 0, then what? Our conclusion would be
So if it doesn't have 0,
mm-hmm.
then that means that there's no difference. Oh, wait, if it has 0, yeah, there's no difference.
So does not contain 0 means there is difference. There is a difference, okay? So there is evidence for difference. So that means we would what? Reject, not reject the null.
We would reject.
Yeah, so our conclusion is we would reject the null, we would accept the alternative. let me try another quick concept here. Okay, so let's say we did a test where you have mu1 minus mu2 equal to 0, and then the alternative, mu1 minus mu2 not equal to 0, and then over here you have the alternative, mu1 minus mu2 greater than 0, and over here you have the alternative, mu1 minus mu2 less than 0. So let's say over here your p-value is equal to 0.08. What is your p-value over here? And what's your p-value over here? Can you tell? Okay, so I'm going to give you the answer. The answer is you can't tell these numbers. And why can you not tell what these are? I haven't given you a very important thing, and that's what? I haven't given you the data. Okay? I haven't given you the data. And so over here, you're getting a p-value of 0.08 because the total tail area in two tails adds up to I have 0.04 over here, 0.04 over here, so the total area is 0.08. Okay? Now, with one of these, okay, it depends on what our data looks like. Okay? If our data ends up over here, then I would shade everything to the right. So the answer over here could be 0.04 or 0.96, depending, and that applies over here. Depending on the data, I would have to do a directionality check. Okay? And so if the directionality lines up of my data, lines up with this alternative, then I would use the 0.04. If it doesn't, I would not reject the null, and I would actually have the p-value of 0.96. Okay? So remember, if I'm saying, do I have evidence, we could, the null hypothesis over here would be, could, for example, be, do we have evidence that the mean heights of men and women are different? And we go through the test. Yeah, probably. We have evidence that the mean heights of men and women are different. If I ask, do I have evidence that the mean height of women is taller than the mean height of men, that would not line up. Our data would not line up with this alternative. I probably would not have evidence. I would not have evidence that the mean height of women is taller than the mean height of men. But over here, if I say, do I have evidence that the mean height of women is shorter than the mean height of men, then the directionality would line up, of our data would line up, and I would be able to, my p-value would just be the area in one of the tails. Okay, so I guess let that just be a reminder to check the directionality of your tests and make sure it makes sense. Okay, so we'll say that. All right. Make sure you know the hypotheses know the appropriate hypotheses for all the tests. Okay, so you have t-test for independent groups. And your null and alternative hypothesis is mu1 minus mu2 equals 0 versus the alternative mu1 minus mu2 doesn't equal 0. And all of these could have a greater than or less than. Directional hypotheses are allowed. Directional versions too. Okay, then we have the t-test for paired data. Your null hypothesis is that the mean difference is equal to 0, and the alternative is that the mean difference doesn't equal 0, and along with the directional versions. How do I? Let's see. Okay, and then we have, what else do I have? Okay, chi-squared goodness of fit. Okay, the null hypothesis is that proportion 1 is equal to some number. I'm making up numbers. Okay, and then the alternative is at least one proportion is wrong. Directional alternative only allowed. Okay, I guess you could also do a chi-squared goodness of fit test. So this one, if you have 3 categories, there's no directional alternative. Chi-squared goodness of fit for only 2 categories could be, null hypothesis is that p is equal to 0.6, and the alternative would be that p is greater than 0.6, okay? If you have 2 categories, you can just say p is the proportion for one of those categories, because this p equal to 0.6 implies that the other category is 0.4. And p greater than 0.6 implies that the other one is less than 0.4. So this one would be directional is allowed only for 2 categories. Yeah, there's no directional alternative when you have 3 categories. Okay, you can only have a directional alternative when you have 2 categories. All right, we'll do a chi-squared test for independence. And the null hypothesis could be rewritten as probability of A given B is equal to the probability of A given not B, or the B complement. And then the alternative would be probability of A given B, doesn't equal that. And directional alternatives are allowed. If degrees of freedom equals 1, implying 2 by 2 table. So if you have a 2 by 2 table, you can have directional alternative. Oops. Let's see. ANOVA. Okay, or one-way ANOVA. mu1 equal to mu2 equal to mu3. Alternative, at least one mu different. Okay, and again, if you have more than 2, you will not have any directional alternatives. And let's do for correlation. The null hypothesis here is that rho is equal to 0 and the alternative rho doesn't equal 0, okay? And directional alternatives allowed. Let's see. Okay, so a large portion will be carrying out each of these statistical tests. Do you have any questions for any particular test? Any details that need to be covered, or
Maybe the goodness of fit.
goodness of fit? Okay.
Proportions versus why they're not mean.
Why they're
Why it's not like mean 1 equals 0.5 versus.
Oh, okay, yeah, because so goodness of fit is when we're dealing with a categorical variable, so we're only going to have counts. We won't have any means, because it might be, for example, it could be, the colors of a flower, and we've got red flowers and white flowers and yellow flowers or something like that. So when we're talking about colors of a flower, it doesn't make sense to have the mean there, okay? Because it's just categories. So, but yes, we can do a quick example here, okay? All right, so let's say we're going to look at colors of a flower. And so your null hypothesis is that the proportion of red flowers is equal to, let's say, 50%. Proportion of white flowers is equal to 30%. And the proportion of yellow flowers, I'm just making this up, is 20%. Okay. And then the alternative will be at least one proportion is wrong. So let's say your data goes through and you count how many red flowers you have, how many white flowers you have, and how many yellow flowers you have. Okay, and so let's say you get 70 red flowers and 40 white flowers and 40 yellow flowers. Okay, so we have a total of 150 flowers. And we want to know, is this evidence that these proportions are wrong? Okay, so this is what we observed. Our data is our observed data. So let's go through the solving. So what we have is our observed. Let's do our expected numbers. Okay, so the total we have is 150. So the expected red is going to be 150 times, if this proportion is correct, I would multiply that by 0.5 and I would expect to see 75 red flowers. For white, I would expect to see 150 times 0.3. I would expect to see 45 white flowers. And for yellow, I would expect to see 30 yellow flowers. Okay, so my chi-squared statistic is observed minus expected, quantity squared divided by expected. So I do 70 minus 75 squared over 75 plus 45 minus 40 squared over 45 and 40. Oh, I did this wrong. Ignore this. This should be 40 minus 45. 40 minus 30 squared over 30. Okay. So I have 25 over 75 plus 25 over 45 plus 100 over 30. Is that right? I think. I'm gonna grab my calculator. I get 4.22. Okay, and so I have degrees of freedom equal to 2, and we'll go to our chi-squared table. 2 degrees of freedom, and I'm looking at 4.22, which gives me a tail probability between 10 and 20%. All right, is that okay? Okay, and so my conclusion would be, do not reject the null hypothesis. Okay, our data does not provide evidence that our proportions are wrong. Even if we're observing, more yellow flowers than what we expected and fewer of the other colors than we expected. Okay, at this point, it's not enough. If I looked at 1,000 flowers and I still had 70, 40, 700, 400, 400, then yeah, that might be evidence. But at 150 flowers, it's not. I guess it would, if I had 1,500 flowers, 700, 400, 400. So. Good? Yeah, so I would, I think the book has pretty good examples for each of these statistical tests. I would go through some of the examples in the book. Yet make sure you know the hypotheses. Make sure you understand what the p-value implies. So what does it mean that my p-value is between 10 and 20% here? Yeah, so it says, even if we assume that these proportions are correct, okay? If we assume that these proportions that we have in mind are correct, is it possible that just a sample drawn at random ends up looking like this or something even more extreme? And the answer is yes, it's possible. And the probability of us drawing a random sample that looks like this or something more extreme is between 10 and 20%. Even when these proportions up here are the true proportions, okay? Okay. If you guys don't have any further questions, we'll end there. And you do have more questions, absolutely. Yeah.
So what kind of material can we expect from before the exam?
From before the exam, I don't know. What's the difference between an observational study and an experiment? It's going to just be very basic conceptual stuff from before the exam. I'm not going to be having you guys calculate, do a bunch of computations from before the exam. So I won't have you figure out binomial probabilities or normal approximation to the binomial or any of that kind of stuff, okay? But I might ask some conceptual stuff, like, you know, when you pick a sample to generalize to the population, what must be true about the sample? And it needs to be representative of the population. Okay. Or so randomly chosen actually is not the requirement. It's randomly chosen helps us get a representative sample, but it's not required, okay, to get a representative sample if you want to generalize. But a lot of our tests are under the assumption that things are random. That's how we do the math, underlying math behind them. But in terms of making your conclusions generalizable to the population, it doesn't have to be random. It just needs to be representative.
What about box plots?
Not on the final. I mean, you should know those for life.
Yeah.
But I don't have box plot questions on the final. Yeah. Okay. All right. Well, good luck as you guys study. We'll see you guys
Thank you.
on Thursday.
Thank you